Okay, we should be live now. How's it going? What's up? We've got another one of these weird little practice sessions. Here's the second one. We're going to be working some number theory and logic exercises while watching YouTube. So I'm going to shut up and I'm going to work some problems. I hope you enjoy and happy studying. Let's get some math done together, y'all. This video is by friend of the channel, Leo Lectures, and it is a really cool video about the Zermelo-Fraenkel axiom system. And yeah, so it's about the axioms that we all use in mathematics. It's some pretty hardcore stuff. I'll understand some of it. I think some of it will go over my head. We can listen to it while doing much easier math. So enjoy.
Alright, in this video I'm going to talk about the Zermelo-Fraenkel choice axioms, what axioms are, what assumptions are in mathematics, and all of these other things, and at the end of it I'm going to solve a Millennium Prize problem. Now that isn't a joke, but bonus points if you can guess which Millennium Prize problem we're going to solve. So to start out, we're going to start out by reviewing what math even is and what axioms are. So what is mathematics? In mathematics, you're basically trying to prove statements, and the way you do this is you start from earlier statements, earlier mathematical statements or theorems, and you use those and combine them using logic to prove new ones. But if you notice, that process has to start somewhere, and where that starts in the case of most of standard mathematics is with the Zermelo-Fraenkel axioms. So this gets to a question of what are axioms. The simplest definition is axioms are just mathematical statements, sort of like any other mathematical statement, but sort of how we relate to them is different, because they're mathematical statements that we take as true without having proof. So they're the starting blocks that we use to combine together to prove all of the rest of stuff in mathematics. And so they're things that feel like they should be obviously true. And so there are things like there's an axiom that says the empty set exists, which is more or less saying like any set exists. And there are axioms that say, okay, two sets, collections of things are equal to each other if their elements are equal to each other. And we can have all of these axioms, and the details of what the axioms are doesn't matter all that much, but I'm actually going to say, like, as much as you need to remember them, there are kind of three types of axioms. So the first type of axiom is existence axioms. And these sort of say, well, we're working in some mathematical world. It would be great if things existed at all, because you could make all these rules of what you can do with your mathematical objects, but if there are no objects, then there's not much you can do. So the existence ones, there are two of them. There's the axiom of the empty set, which is this one, so empty set axiom. And then there's an axiom of infinity. And without the axiom of infinity, you could imagine a mathematical world where every object only had up to a finite size. And so these are the only two axioms that you need to start building your entire mathematical universe, with the second type of axiom, which I'm going to call building axioms. So these axioms, now that you have two things exist, you have a set with no elements and you have a set with infinitely many elements, the next thing to do is to start making more stuff. So for example, you have the schema separation, which lets you do set comprehension. You have the axiom of pairing that lets you go from two sets A and B and get A comma B. You have union. You have power set, the set of all subsets. You have the axiom of choice, which I'll have an entire separate video on. And you have the schema of replacement. And so you'll notice most of these are just rules for how you can take existing sets and make new ones. And a lot of these, like for example, you need union, power set, and replacement to make bigger and bigger infinities. And separation lets you do set comprehension, which is very useful for making certain kinds of sets. And then the third type of ZFC axiom you could call like niceness, or like good properties, or regularity. And so what this says is that our sets kind of behave well. And so the first axiom here, axiom 1 of extension, that says, you know, A is equal to B if and only if every element in A is also an element of B. And so it says equality is determined by the elements. And the other niceness property, well-foundedness, this is secretly the axiom that presents problems like Russell's paradox. The axiom of foundation sort of prevents you from having these logical loops. So there are three types. There are two existence axioms that tell you have an empty set and you have an infinite set. There are 8 axioms that we take as standard that let you, starting with some sets, build new in other sets. And there are 2 nice properties that let you say that everything behaves well, that things don't get weird in your mathematical universe, because without these axioms, you can have weird stuff, but that's an entirely different world. And so what axioms are these mathematical statements that we take to be true in of themselves. They should be simple. They should be conservative. You don't want to assume too much, because if you assume too much, like Zermelo did with earlier axioms, with an axiom called general comprehension, you could make a contradiction and you could break all of mathematics. But you also don't want to assume too much, because you don't want to assume something that isn't true. And this is kind of like a vaguish philosophical notion of like, well, what is true or what isn't true? Is there some Platonic idea of what should be true and what shouldn't be? And that's like, there are many arguments about that. But why we are so conservative with the axioms is that, like, okay, you know, maybe we can't tell whether certain things are true, like the continuum hypothesis, but we certainly don't want to make an assumption that leads to some consequences that certainly are untrue. But people have arguments about that, like, should the axiom of choice be assumed? And I'll talk about that more in that video, because there are some consequences of it that feel untrue, that they feel wrong. And so axioms, there is a bit of arbitrariness, but for the most part, these axioms are strong enough to build all of mathematics. You can do number theory, you can do differential geometry or differential equations, you can do computer science and talk about computability. All of that can be encoded in these sets. And I guess it's useful just knowing that they're out there. Going into the details, even if you're a mathematician, of these axioms is usually not that useful unless you're a set theorist or you're doing something in like category theory where set theory problems come up. But it is good to know that at least there is some foundation and a general idea of how it works, and you can just read this list of axioms and see how it works. Now, the next thing I want to talk about is assumptions. Assumptions are just mathematical statements. There's, in a kind of technical sense, no difference between an axiom, an assumption, and a mathematical statement. And if you go to Wikipedia for axiom, they'll say axioms, postulates, and assumptions, and they're all the same thing. But really where they differ is that how we as a mathematical community treat them and how we use this language. And so generally, although assumptions are mathematical statements like axioms, and they're mathematical statements that when we use them without proof, the way we feel about them is very different. Usually assumptions are things that we hope to be able to prove later, but can't prove now, but it'd still be useful for it to be true. And so one of the most common assumptions that I've seen around doing mathematical cryptography is the existence of what are called one-way functions. I'll call this assumption OWF. And this is a class of functions that is basically necessary to have any security proof that one-way functions must exist in any of cryptography. And the thing is, one-way functions, the existence of them, if you could prove that they exist, this is a much stronger statement than proving P is not equal to NP. And we're not even close to proving this. Like, some people think we're, I don't know, it could be 100 years out from proving P is not equal to NP. And just the existence of one-way functions is so strong that you could prove in one line that P is not equal to NP, and we're going to do that at the end of this video. And the things that you need one-way functions, like, for example, just the assumption that RSA works, which is the standard asymmetric encryption scheme, would imply that one-way functions exist. The existence of collision-resistant hash functions that you would use for making something like a proof-of-work scheme, like maybe you're trying to make your own cryptocurrency and you're doing something like what Bitcoin does. That would also assume that one-way functions exist. There's a whole world of lattice space assumptions, so learning with error, or shortest vector problems. And these are basically, we kind of joke that there's only two hard problems that we have an idea about, and that's factoring and lattice problems. And factoring is broken by quantum computing. But these lattice problems, they might be broken by quantum computing. I actually wouldn't be surprised if they are. But so far, we haven't broken them. And so the game in cryptography, because we're so far from our mathematics being able to prove security from the axioms from ZFC, is that we try to make an assumption that is sort of well defended. So for example, the assumption that one-way functions exist is something that we've used for a long time, and we try to base all of our cryptography on that one assumption, so that, you know, over the decades, as this is tested and as many people try to find ways to break it, what we do is that even though our foundation isn't based upon the ZFCs, we have this one extra assumption, say that one-way functions exist, or some things like lattice problems, and that if we can break any crypto system, it would also mean it would break this assumption. And so other assumptions are used in mathematics as well. Like, for example, we have a thing called the generalized Riemann hypothesis, which has to do with these things called L functions. And I actually get these confused sometimes, but there's also a thing called the extended Riemann hypothesis. In my head, these two were opposite from each other. I had the names wrong. And this sort of says the regular Riemann hypothesis is for the integers, and the extended Riemann hypothesis is a similar thing, but for all of these different types of integers. Like, you can imagine the integers where you join I, or if you're looking for details of this, these are things called algebraic integers. And there's actually infinitely many other Riemann hypotheses. And there's a lot of number theory that, you know, who knows how far we are away from proving the Riemann hypothesis or from all of these other Riemann hypotheses, but we can do a lot of math under the assumption that the generalized Riemann hypothesis holds or the extended Riemann hypothesis holds. So assumptions, although they're technically the same as axioms in that they're mathematical statements that when we use them, we assume them without proof, the way we treat them is very different in that we don't think of them as inherently true in of themselves. We think of them things as almost like aspirations or conjectures that we hope to be able to prove later. So going to the next page. Philosophy of axioms. Yes, so now I'm about to contradict and give yet another way to think of axioms. So again, all of these things, axioms and assumptions, are mathematical statements. A third way to think about axioms is that instead of being like, okay, these are things that we think are inherently true, we think of them as like, well, we could imagine a world where they're true. And so this is maybe you could call the philosophically agnostic approach to axioms. So this way, instead of an axiom being, so it's still a statement that is true or taken as true without proof. But now instead we're kind of thinking of it as like, well, instead of taking this as a statement that we really think is true because it's self-evident, we're just saying, well, what if we just imagine a world with a logic with this being true? And so we do that a lot with kind of non-standard examples of things. So for example, there's a way to take the axioms of, say, Euclidean geometry. And one, important axiom in plain Euclidean geometry is if I have 2 points, if I have a line through one, there's one line that's parallel to this line through another point. But you could just have a different axiom for that. You could say, well, instead, if I had a point and I have another point and there's a line, well, maybe there's 2 parallel lines. And then you get to things called non-Euclidean geometries. And the Euclidean geometries. And what you might think is that, well, the non-Euclidean geometry is wrong because I live in the real world, and in the real world, if I have a plane or say I have a flat piece of paper and I draw a line through a point that's parallel to another line, there's only one of those lines. But there are situations where non-Euclidean geometries inherently come up in the mathematical world, and so they're just sort of, we're not thinking of them as the true world, we're thinking of them as a different world. Like here's a world where non-Euclidean geometries could exist. Other things that one might have, I have listed here Archimedean versus non-Archimedean fields, and this is where you can have things which are infinitely small, and this gives rise to things like you could have the regular real numbers versus things like the p-adic numbers. And again, one might say it's like, well, the real numbers, they're called real numbers. Those are the real ones. But p-adic numbers, they come up in number theory and all throughout algebra, and they're useful in of themselves, even if they feel like different numbers. Another example that I'll talk about more in the axiom of choice video is that you might have something like, if you're doing set theory again, you might throw out the axiom of choice and instead have the axiom of determinacy. And the axiom of determinacy basically says if I have a competitive combinatorial game, what you should picture is something like chess, where two people are making moves, but instead I allow the game to last infinitely long, countable infinity. The axiom of determinacy says all of those combinatorial games, they inherently have one person who always wins. And that's true with finite games, but that's not true if you assume the axiom of choice. And so you can imagine a different world where the axiom of choice isn't true, where the axiom of determinacy is true, and that all of these games hold, that there's always a winner. And in that world, you might have something else, like you might have every subset is Lebesgue measurable. And this is, in mathematics, Lebesgue measurability is kind of how we think of the mass of subsets of like Rn. In practice, when you're doing analysis and you have to do integrals over weird domains, you have to do a lot of bookkeeping, and it's kind of a bit of a headache to keep track of whether you can integrate over some set or some function or not. But in this world where choice doesn't hold, you might not have to do any of that bookkeeping, and maybe there are other properties which are nice. And so this second idea is that instead of saying axioms are things that like we're talking about the real world, like a Platonic idea, we just say it's like, there could be lots of worlds. There could be lots of different ways of doing mathematics, and we just take axioms as our starting block, and we can redo mathematics with any set of axioms. You can come up with your own set of axioms and just see what happens and see if interesting things come out of it. And so that's kind of the two ways you can think of axioms, as the Platonic way and as the game way. Now, what do mathematicians think? I think most mathematicians really think in terms of the Platonic way, that there is a real world of like real Platonic ideas, and we're trying to find axioms that describes that real world. But that we also, when we're doing non-standards things, like say axiom of determinacy or all of these weird axiomatizations, we're thinking of those as almost their own logical objects. And we can think of those as just sort of different logic games that have their own consequences and may be true in that world. And so for the last thing, I'm going to prove P is not equal to NP. Now, this isn't the hardest thing to do. I think the hardest part of this is remembering the definition of a one-way function. So a one-way function, if I remember correctly, is a function f from inputs, which you could call bit strings to bit strings. So this is really like a computable function. You're going from like 0, 1, 1, 0, blah 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 to other things. Basically inputs and outputs on a computer. And it has this property. If I give it a random input, I'm going to be a little loose here. So I give it some random input and sufficiently random distribution, and I tell someone f of r, then if that person, say that person is polynomial time Turing machine, so a computer that runs efficiently, that also has access to randomness, so it can also flip coins. So we'll put another P for probabilistic polynomial time Turing machine. Then M cannot guess or find inputs X reliably such that f of X equals f of R. So this is the one-way notion, that you can go from an input, a random input, which is important, to an output, and a reasonable machine M will not be able to find an inverse. You could see why this might be useful and how you could start building cryptography out of this. And so now we're going to prove that if we had the axiom of one-way functions exists, we can prove that P is not equal to NP. And the way we're going to prove that is we're actually going to start and do it in the opposite direction. We're going to say if P equals NP, then one-way functions don't exist. So let's suppose we have some function f, and you can compute it in polynomial time, in poly time. And we want to show that no matter what, f is not a one-way function. So we're going to make some computer inv, which finds inverses. And here's how we're going to do it. We're going to note that this problem, the predicate f of, we're going to call the predicate p, comma, some outputs, let's call it h. And this problem that says, is there some input r with predicate p, so like let's say this is the first 10 bits, with the first 10 bits of r, such that f of r equals h. This is something that no matter what, this is an NP problem. To go into the details of this, is the reason it's an NP problem is because I can verify that it's true or false in polynomial time. And so if I have this predicate problem, I can easily find an inverse to any input. So if I start with some x, and I produce an f of x, and then I give that to someone else as a challenge, find some inverse of f of x, here's what they would do. Well, they would check first the predicate under f of 0, comma f of x. Basically say, is there some input that starts with a 0 that if I were to apply f, I would get I would get f of x. And say the answer is no. Well, if the answer is no, then I just check, okay, predicate f1, comma f of x. And the answer actually will be always yes if I check it for 0, and I get no. And essentially what I will end up doing is I'll do a binary search. So I'll check the first digit, and I'll see, okay, the first digit has to be a 1. And then I'll check predicates for 1, 0, and 1, 1. And let's say I find this second digit has to be a 0. Okay, then I'll check 1, 0, 1, and then I'll check 1, 0, 0. And say it goes down this way. And I'll just keep doing this, checking predicates, until I get an input that's long enough, and this will happen in polynomial time, that gives me some x prime, which might not be equal to x. It might not find this preimage, but it will always find a preimage because 1 exists, x exists, and it will give me an inverse to f of x, and that will prove that f is not a one-way function. And that algorithm gives me an inverter. So if p is equal to np, there are no one-way functions. So if there are one-way functions, p is not equal to np. And I did look up right before this the rules for the Millennium Prize problem. It says, well, it has to be accepted in some journal and it has to be reputable. It's like, well, there's lots and lots of mathematical cryptography papers that assume one-way functions exist. And I think my biggest problem here is that, one, this is an assumption. It's not an axiom. This is not something that we think of as true in of itself. And my second problem is, even if we did think of one-way functions as existing in of themselves, I'm not the first person to notice this. This is something that anybody who does any mathematical cryptography would be able to make this proof sort of off the cuff. And so to review, what are the things to know? I'll go all the way back to the first slide. Well, the first thing to know is that ZFC is a set of axioms that makes up our first mathematical statements that we base all the rest of mathematics on, and we make it out of sets. Axioms are statements that, if we're thinking of them in the Platonic way, they're just things that we think of as self-evidently true, because we have to start somewhere to be able to prove things. We have to start with some statements that have enough power to be able to prove more things, but aren't too powerful that we get contradictions, because early on in Foundations, Zermelo's first textbook he wrote had an axiom that produced a contradiction, and it was a big problem, and so had to kind of adjust things. I talked about the three types of axioms. We need that any objects exist, we need to make more mathematical objects, and we need those objects to be suitably well behaved. Talked about assumptions. In cryptography or in a bunch of fields of mathematics, assumptions aren't used extremely often. Sometimes they're often used that say, assuming this, if we can prove this conjecture, we can prove that. But in some mathematical fields like cryptography, to do anything you have to have assumptions, and so they're used all the time. The second definition of axioms is the non-Platonic way to look at axioms, which is to say, who cares what the real world is? There's a bunch of worlds. We can have Euclidean geometry, we can have non-Euclidean geometry, Archimedean geometries, non-Archimedean geometries. We can do a bunch of stuff. And they're all interesting, and we should look at them, and they are all interesting. And that gives us our sort of two philosophies on axioms. And if you have a suitably strong assumption, you can solve a Millennium Prize problem, $1 million problem, that otherwise, without the assumption, would take maybe the next 100 years to solve. And so that's another reason to be a little conservative with the axioms. So I went over this kind of quickly because I just wanted to give an overview of what axioms, assumptions, and ZFC are. If you have any questions, let me know. I'm just sort of starting out doing this. And yeah, I guess that's it for this one. All right. We're finally here. The axiom of choice, the boogeyman of mathematics.
All right, that was an interesting video. I really enjoyed that. Thank you, Leo Lectures, for sending that one in. I learned a lot. I think that was super, super interesting. I mean, I only listened to it, obviously, in the background. I didn't completely understand everything, but yeah, that was cool. I enjoyed it. I want to get another one of these, like, really ridiculous, what's his name? City tutoring. This guy's so freaking funny. Let's get another one from this guy. I want to hear about the calculus textbooks.
Of biology and Hello everyone, Alfred Cromwell here, the founder and president of City Tutoring, here and speaking to you from
funny.
Lynch.
Like, this dude is so funny. He is not real. There's no way.
Because a lot of students, a lot of you have asked me, what mathematics, what calculus books are we using, do I use at City Tutoring for the students who want to take extra calculus reinforcement? And before I said students, by the way, I should have said survivors of this, because in a way, all of you watching me, unless you're an instructor, I know a lot of instructors watch me, but I know I get watched by a lot of students as well. And a lot of you are survivors. You're survivors of this modern, what they call modern, educational system. And so it's really, I'm always pleased to be addressing you as always, because I feel like I'm standing before a sea of young minds that are, your potential is unfulfilled in a way, but you have potential. And it's also a tragedy because most of you have been led astray by the glossy pages of mediocrity that parade as calculus textbooks in this era. We're living in an era of, my impression is there's certainly been a decline of standards. all across the board, not just the decline of moral standards, which has been, the moral standards kind of changed throughout history. But what I'm referring to is more of a decline in reasoning, an intellectual decline, if you will. And yes, I'm referring to a lot of the modern textbooks, like the James Stewarts. And then back in the 90s, and we still have some of it today, some echoes today, we have the Reformist Drivel of Hughes Hallett. And these books were, in a way, the harbingers of the apocalypse in math education that we're seeing. And oftentimes you'll find they promise you simplicity, but at what cost? And the soul of calculus itself. And oftentimes they've traded depth for diagrams that are totally not needed. They've traded rigor for relatability and the elegance for exercises that make you feel good about yourselves without actually with knowing absolutely nothing, right? So, in fact, I suspect some of you even enjoy them. Of course you do, some of you. Because, oftentimes when you don't have sufficient mathematical maturity, you tend to be tempted by these feel-good strategies, right? It's kind of like almost like a child when they enjoy sugary cereal. It's perhaps sweet, but it leaves you empty within an hour. So, and of course, no nutrients to speak of. And when I was personally an undergraduate, you saw the influence of Stewart calculus. But we used, in my particular program, I'm very blessed because we used Michael Spivak's calculus. It's a text that really will separate the true mathematicians from the dabblers. And Spivak does not spoon feed you. And he serves you a banquet of proofs and demands that you bring your appetite for rigor. He doesn't coddle you with colorful graphics of roller coasters to explain derivatives. And he assumes that if you do not already know what a roller coaster is, you should not be studying calculus in the first place, right? But here we are. We are in an era where even the word proof has been sort of relegated to the appendix, as though it were almost like an embarrassing secret. And these modern books that claim to make calculus accessible, but what they truly do is debase the material. They reduce the great edifice of mathematical thought, and it gives me the impression of almost like a prefabricated IKEA bookshelf, right? And I don't say that lightly. I don't like IKEA at all. So it's easy to assemble, perhaps, but woe unto anyone who leans on it, right? And we're already seeing things that are in many of the textbooks also. The proofs have been sacrificed completely, in fact. I was just recently talking to a student at a local college, and he mentioned to me that the only thing they do is learn mechanisms. They learn basically computational stuff, which is fine. I'm not against computation, much to the contrary. We could all use more computational exercises, but when you sacrifice rigor, then we do have a problem. And the struggle in math, I keep saying this over and over, you're not going to become good at math if you have an aversion to struggle. And struggle is precisely what these modern texts seek to avoid. You've got authors in their so-called benevolence. They're not really being benevolent, but they perceive themselves as such. And they have decided that you, the students, that you're too delicate for rigor. For example, that the epsilon delta definition of a limit is too intimidating. I've actually heard people tell me that. And yes, I know the Stewart textbook has it. Before you even say anything, I know you're going to say, well, the Stewart textbook has the epsilon delta definition. But how many of your instructors are actually making you prove it that way? You can let me know in the comments. Maybe I'm wrong, but I have not seen it recently. And they make an assumption that you cannot handle abstraction. And so they give you pretty pictures, perhaps. I don't find them pretty, but some of you might. And they give you the so-called applications. They're really mindless applications about population growth, interest rates, as though the calculus were merely the handmaiden of biology and economists, or heaven forbid, engineers. Heaven forbid that we ever become, that pure mathematics becomes the handmaiden of applied, so-called applied mathematicians. But calculus itself is not the servant of the sciences. It's really their sovereign. It's how God communicates certain rational, logical language of the universe. And it was spoken fluently by Newton, Leibniz, and the select few who refused to bow down to the tyranny of the mediocre. Do you think, if you think about, if you're interested in history, do you think Newton would have written his great work, the Principia, if they gave him a copy of Stewart's Calculus? He would have probably burned it, and at that point, I think he would have been highly offended, among other things, to read something like Stewart's Calculus. Now, you might find that what I'm saying is harsh, and that's good. I expect you to. Mathematics is harsh. It's not a democracy. Math doesn't care. Truth doesn't care about your feelings. And we're living in an age where people try to put their feelings above reason. And we even see it sometimes even in the churches. We see that in some instances where theology is replaced by sort of feel-good stuff. But there's a paradox here, because it's also the purest form of truth and beauty that you will ever encounter in our human system. But only if you're willing to wrestle with it, to struggle, to fail, to rise again. In that struggle, you find certain transcendence. It's meant to be a struggle. So you put away your candy-coated textbooks. Buy a copy of Spivak, even Apostle. I like Tom Apostle in a different way, although I prefer Spivak personally in terms of style, but Apostle is fine. Don't let yourself be deceived by the false prophets of reform calculus. They do not wish to teach you math. The only effect that will have is to make you comfortable within your own ignorance. And comfort is the great enemy of greatness. And mathematics, real mathematics, is nothing short of greatness. It is really a cathedral of thought. It's built from a foundation, theorem by theorem, over centuries. And every time that you crack open some of these textbooks, I feel like you chip away at the foundation. So we need to do better, demand better, and be better. And on that note, thank you. And I will be sharing with you the books that I use at City Tutoring because I use a variety of books, but some of the books that I use, it really all depends on the level of the student, right? It's very important to understand what level, what background you've come from. Because, for example, it's not the same to teach someone who is taking AP calculus versus someone who just wants, let's say, they're already in college and they want a bit more of a rigorous foundation. Most students are struggling with Stewart even. They struggle because they don't understand. Again, what do I keep saying in all my videos? Again and again and again, the why. Why do you do something a certain way? If you don't understand the why, then you could do all the computation you want, but you're lost. I had a student the other day right here in my office, and he was standing there and he said, he was amazed at just how bad the gaps in his knowledge were. So anyway, I'll show you the books. I don't have the physical copies here. I have them in my office, but I'm going to show you the titles in case you're interested and kind of give you some background on them. Thank you. All right, so these are the two books that we use here that I've been using a lot in the past several semesters here at City Tutoring. It varies between Calculus, a complete course by Robert Adams and Christopher Essex. And I've been using Spivak Calculus, the 4th edition. Now, a couple of disclaimers here. A lot of the times it varies. These are the books that I use mostly with my college students. I also have college students who come to me. They are already taking courses at the local schools, the local colleges. But the reason they come to City Tutoring is because they want actual, either one-to-one, or they want a setting in which it's more structured, like we do at City Tutoring. So they want to be challenged a little bit more, and they want to take their math a lot more seriously. So we tend to use Spivak for that group. But then I also get Calculus by Robert Adams and Christopher Essex. Is a book that I like their approach also, even though they're more, a lot of engineers use their book. But I like a lot of their approach to the material as well, especially if you're looking for more of a computational sort of problem set, because they also do proofs though. So I don't have a problem with that. I like that they do proofs and they give you the computational exercises. Some of the problems are actually very, very good quality. So those are the 2 books that I mostly use. I have 2 or 3 other books that I also use for calculus, because some of the students, they're doing advanced placement. That's at the high school level. So at the high school level, we tend to switch up things depending on the level testing of the group. I've used, depending on the group, if it's just a college prep course, we've used Saxon's calculus, because Saxon has a incremental approach, a spiral approach that I quite like. And of course, sometimes we use the British materials from Edexcel. We use some of the British material. So some of the manuals that they have for calculus level, pure mathematics as well. So it really just depends. But these books, I strongly recommend. One of the
In 1637, imagine a map of the mathematical world. It's the product of thousands of years of human ingenuity, from the Babylonians to Riemann to the present day. In this world is everything we know about numbers, shapes, and their relationships. There are many mathematical continents, each with its own language and culture. One with a distinguished history is number theory. It's an unpredictable land of lush forests full of opportunity, with little secrets hidden everywhere. Here, they speak the language of arithmetic. Another continent is called harmonic analysis. It's a place of smooth curves, symmetry, and repeating patterns. Here, mathematical objects speak the language of signals and waves. For most of history, these 2 continents have remained distant strangers. Mathematicians didn't think there would be much to gain from trying to travel between them. But in the last half-century, something striking has happened. We've discovered glimpses of an enormous bridge that seems to connect the continents. As mathematicians build segments of this bridge, they can pass seemingly intractable problems across it, illuminating them in the process. The full bridge is called the Langlands program. It's one of the biggest projects in modern mathematical research. Some even like to call it a grand unified theory of mathematics. I'm Alex Kontorovich, and I'll be your guide as we explore some of the patterns and symmetries suggested by the Langlands program. Ideas that imply deep, powerful, and beautiful connections between the most fundamental continents of the mathematical world. In 1967, a 30-year-old mathematician named Robert Langlands wrote a deceptively modest letter to his colleague, the famous French number theorist André Weil. If you are willing to read this as pure speculation, I would appreciate that, the letter said. If not, I'm sure you have a wastebasket handy. To Weil's surprise, the letter contained a series of striking conjectures that predicted something very unlikely: a correspondence between 2 objects from completely different fields of math. What Langlands suggested seemed stranger than telepathy. How could 2 objects indigenous to different mathematical continents evolve to behave in exactly the same way? This is the question at the heart of the Langlands program. To understand this mysterious connection, we first have to meet 2 mathematicians who studied these objects from opposite shores. This is Srinivasa Ramanujan. In 1916, the self-taught Indian math prodigy got very interested in a particular function, now known as the Ramanujan discriminant function. Put simply, this function multiplies infinitely many terms together. In Ramanujan's time, this was already known to be a special type of function called a modular form. To see modular forms, it's not enough to look at the real numbers. We need to treat the input as a complex number, which will produce a complex output. When we do this, the function starts to reveal its mesmerizing symmetries. Modular forms are some of the most bizarre objects in mathematics. They satisfy so many internal symmetries that it's surprising that they exist at all. Ramanujan wasn't the first to study the symmetries of modular forms, but he was the first to imagine whether they had any connection to the distant shores of number theory. He did this by studying the function from a different angle. What would happen, Ramanujan wanted to know, if you multiplied all of its terms out and collected the coefficients? When he did this, Ramanujan noticed that the coefficients have a special kind of predictive power. If you know all of the function's prime coefficients, then you can use them to figure out the rest. For example, if you find this coefficient, which is negative 24, and this coefficient, which happens to be 252, then I can immediately tell you what the coefficient of x to the sixth will be, because 2 times 3 is 6. This pattern always seemed to hold, but Ramanujan couldn't prove why. He became obsessed with these numbers and continued to experiment with them, eventually making more remarkable conjectures on their behavior. But they were so difficult to prove that they sat collecting dust. Nearly 6 decades later, Belgian mathematician Pierre Deligne came up with a brilliant proof of Ramanujan's conjecture, earning Deligne a Fields Medal. Deligne used the key insight from Langland's conjectures, called functoriality, to bypass the bridge from harmonic analysis to number theory. But the bridge goes in both directions. Now, it's time to travel over to the shores of number theory, where the rest of our story will take shape. In 1637, the French lawyer turned hobbyist mathematician Pierre de Fermat scribbled an equation in his copy of Diophantus's Arithmetica. He never offered a proof, claiming that it was too marvelous for the narrow margins to contain. The theorem featured a polynomial equation, a fundamental object native to the continent of number theory. These are some of the most basic equations you can write down, just variables with exponents that are positive whole numbers. You may remember the Pythagorean theorem from school, that a right triangle with sides A, B, and hypotenuse C will satisfy this equation. There are lots of integer solutions. Here's the note that Fermat wrote in the margins of Arithmetica. Unlike the Pythagorean theorem, these polynomial equations will never have natural number solutions, except of course if one of the variables is 0. This tantalizingly simple claim came to be known as Fermat's last theorem. For 350 years, generations of mathematicians struggled to prove or disprove this conjecture. Then, in the 1990s, Princeton mathematician Andrew Wiles shocked the world with a breakthrough. Standing on the shores of number theory, he began dreaming of a bridge to harmonic analysis. To understand how Wiles built this bridge, we'll first need to meet a special type of polynomial equation called an elliptic curve. Here's an example of an elliptic curve. You'll notice that it only has two variables, x and y. Let's take a look at our elliptic curve graphed on the Cartesian plane. This shows all the pairs of real numbers x and y that satisfy our equation. But we're not just interested in the real solutions. We also want to make the problem more interesting by restricting the domain to find solutions in the rational numbers, that is, fractions, and in the integers. To study these solutions, it's useful to consider our elliptic curve from another perspective. We can use a fantastic tool from number theory called modular arithmetic. It's a way of counting integers using only the remainders. We use this kind of math every day when we tell time on a 12-hour clock. If someone says, let's meet at 1500, you know they really mean 3 p.m. because both 15.
Okay, y'all, that's it for today. I gotta go. Thank you for watching. This has been fun for me. I hope you enjoyed this. It's it's a different kind of format. It's a way that I can actually like just sort of zone in and do a little bit of math and show what that's like on my